All right, so lesson 3 is on functions and their properties. So we have a definition of a function that your book has. It says a function f from a set A to B is a relation that assigns each element x in a set A to exactly one element y in the set B. So that means that if you have, an x value of 2, there's only one y value that goes with it. Maybe you have 2, 4, but you're not also going to have 2, -4. Okay, it's kind of a difficult definition to remember. So the easiest way to remember if something's a function or not a function is by the vertical line test. So if you remember the vertical line test, you're just going to take a bunch of vertical lines through your possibility of a function, and it's going to cross at only one point for every single vertical line. Okay, so the second example says not a function because there are actually 3 places where it's crossing. So it means it would have like the point 2, 0, 2, 2, 2, 5. It would have multiple things that have the same x value. Okay, so that would not be a function. All right, so number 1, so it says decide whether the following equations represent y as a function of x. And it says if you do not know the shape of the function, you might want to try a t-table to graph it. Okay, so the first one that we have is x squared plus y squared equals 4. Does anybody know what this is? What shape is it? Yeah, Lauren. It is a circle because it's in the form x minus h squared plus y minus k squared equals r squared. So it may have been a while since we've talked about circles, but it's in a circle form. So the center is 0, 0, and your radius is 2. So the graph looks like this. All right. So is it a function then? No, it is not. Exactly. So not a function. So if you didn't know that, you could maybe try a couple points and try to figure out what it is. Another thing that you could do is you could try to solve for y in order to graph, right? So if you're solving for y, what happens is you subtract the x squared over, and you have equals y squared, right? 4 minus x squared equals y squared. And then you take the square root of both sides. But we know that whenever you take a square root, we write plus or minus. So we have y equals plus or minus the square root of 4 minus x squared. So what this means is, as I'm plugging in any point, let's say I plug in 1, I would get both root 3, but I would also get negative root 3 as well. Okay, so by definition, that's not a function because I can plug in 1 and get 2 outputs. Okay, they always talk about in like Algebra 1 books, a function machine. You input something and you get one thing out. So that's one where you would get multiple things out. Okay, so if I have x equals y squared, anybody know what shape this is? Yes, Emerson? Ah. It's on its side. It's a parabola, right? It's a sideways parabola. So it looks like this. Exactly. So it's a sideways parabola. So you could do a t-table for this one, but as you're doing the t-table, what you're doing is you're plugging things in for y. That's like your input. And your output would be 4. So see how you have 4, 2, but you also have 4, -2. All right, so this is not a function. All right, so what about this last shape? What shape is this one? A line. You better know that one, right? It's a line. So are lines always functions?
Yes.
Ah, yes, except for... Exactly, yeah, exactly. So lines are functions except when they are vertical lines, and then that's the only one that is not a function. So if you solve for y for this one, you get y equals -2x plus 5. It has a y-intercept of 5 and a slope of -2. So it looks something like that. So yes, this is a function. All right, so that's kind of the easy stuff, just figuring out whether something's a function or not. So now we're going to talk about the functions and their properties, right? So one thing that we always talk about with functions is domain. All right, so the domain convention, so it says unless information to the contrary is given, the domain of the function consists of all x values where the function is defined. So it's going to be everywhere that something's defined. Well, where is something not defined? So when the denominator is equal to 0, it's not defined, right? Undefined. And if you have a square root of a negative number, then it's not defined. So I always tell people to look for square roots and denominators. So really, it's not just square roots. It could be like square roots or even roots you could have. You could also have logarithms. Do you guys remember you can't take the log of a negative number? So logarithms would also have domain issues. So number 1, so we have f of x equals 1 over x minus 4. Okay, so what would be bad is if our denominator was equal to 0. So we're going to set our denominator equal to 0 to see what happens. So we're going to say x minus 4 equals 0, so x equals 4. This is not in the domain. Are there any other things that aren't in the domain? So if I was doing a t-table, can I plug in everything else and get a number out? Yeah, every other thing we do with the t-table, we're going to get some kind of output, right? I could plug in 5 billion. I would get a number out. Right, so 4 is the only thing that gives me undefined. So my domain then is everything except for 4. So I'm going to write it as x is not equal to 4. Now back in Algebra 2, I made you guys do this on a number line. I had you put 4 there. I did an open circle, and we shaded on each side. And then we wrote negative infinity to 4, union 4 to infinity. You can do that if you want, but this is acceptable as well. Isn't that much easier to write? X is not equal to 4. So I'll let you write it like that. All right, so the next one. So we have g of x equals the square root of 16 minus x squared. So if you kind of logic through this one, it will make sense. Think about things that are okay to plug in. Can I plug in 4? Yeah, you can actually take the square root of 0. So yes, that is good. Can I plug in 0? Yeah, square root of 16, that works. What if I plug in 5? Right, it doesn't work. We can't have a negative under a square root. So what we're thinking is, where is 16 minus x squared greater than or equal to 0? Because it's under the square root, right? We can't have negatives. All right, now if we're solving something like this, 16 minus x squared is greater than or equal to 0, we actually have to use what we call critical values. So we did this last year in Algebra 2 when we did quadratic inequalities. So basically we're finding when it's equal to 0. So we're going to factor. So we have 4 minus x, and we have 4 plus x. Or you could have added the x squared to the other side and taken the square root. But you end up getting x equals plus or minus 4. Ed. So we put those on a number line. Remember, didn't I talk about this in senior meetings? So, and we have x could be 4. We said those are allowed. But when you try things on the left and the middle and the right, if I try like negative 5, 16 minus a negative 5 squared is 16 minus 25, right? That doesn't work. So that's bad. And then if I try 5, that's also bad. But we said if we tried 0, it did work. So our shading is directly in between. So our domain, we write, the easiest way to do this one is in interval notation. So negative 4 to 4 bracket. So whenever you have a whole bunch of points like that, intervals, write it in interval notation. You could also write it like negative 4 is less than or equal to x, which is less than or equal to 4. And some of you guys do that, that's fine. Just some people mess up on the inequality signs. I don't know why. You have that cool alligator trick. Why do we mess that up? But people still mess them up. All right, that should say h of t equals 1 over the square root of t plus 5. So you should have h of t, not h of x. All right, so this one has not only a denominator, but also a square root. So there's multiple things going on. So it can't equal 0 because it's on the denominator, and it can't be negative because it's under a square root. Right, so we're going to say that t plus 5, instead of saying greater than or equal to 0, we're just going to say greater than 0 for this one. Because if it was equal to 0, it would be on the denominator, and that would be bad. So we have t is greater than negative 5. So you can leave your domain like that, or you can think, okay, I'm bigger than negative 5, so I'm going to be on the right of that. So it's parentheses negative 5 to infinity. Right, it can't be negative 5. So do you guys see why it can't be negative 5? Right, because that would give the denominator equal to 0. So we do a parenthesis to notate that it can't be negative 5. Otherwise, it would be a bracket. All right, and number 4, this one has a fourth root. Fourth root has the same rules as the square root, right? You can't take the fourth root of a negative number either. What if it had been a cube root? Then it's fine, it could be whatever. So cube roots aren't going to affect your domain. You can still plug in whatever you want if you have a 3 for your root. Okay, but this one's same idea, so we can't have 0 because it's on the denominator, and it has to be positive. So we're going to say that 9x squared minus 4 is greater than 0. So this is another one where we should factor, and we should find the critical values. So we're going to factor into 3x plus 2 times 3x minus 2. We're going to set each piece equal to 0. So we get x equals negative 2/3 and x equals positive 2/3. So those are the things that go on the number line. Those are, something's happening there, right? So we're testing in each location. So again, if you can kind of logic through these, it makes sense. Like if you plug in 0, 0 is bad because you get 9 times 0 squared is 0. Minus 4, you get a negative 4 under there. So that's bad. We can't have a negative 4 under the fourth rule. Okay, so 0 does not work. But if you try like 1, then you have 9 minus 4, that's okay. And if I try negative 1, same thing, it's okay. So we end up getting the ends here, and we're going to have open circles because of the denominator. So our domain is going to be negative infinity to negative 2/3, parenthesis, union, parenthesis, 2/3 to infinity, like that. So you guys all remember interval notation. Yeah. All right, so we talked about zeros of a function the other day, but we were only talking about quadratic functions, so you guys could use the quadratic formula to find it, or you could factor. So the first one is a quadratic function. So if you're finding a 0, it's another name for x-intercept. So we plug in 0 for the y value. So we get 0 equals 3x squared plus x minus 10. And we end up factoring. And I think this one does factor. So we get 3x and x. And then I can see that 10 and 1 aren't going to work. So we're going to do 2 and 5. So we need the 5 on the inside and the 2 on the outside. So we're going to need plus 6 and negative 5 on my outer and inner. So see how the outer is 6x and the inner is negative 5x. That's how they're combining to be 1x. So we set each piece equal to 0 and solve. So we end up getting x equals 5/3 and x equals negative 2. So those are x-intercepts. Those are points. The way they're set up, though, when I say x equals negative 2, it kind of makes you think of a vertical line, x equals negative 2. So I usually have people write them as points, like 5/3, comma 0, and negative 2, comma 0. Because we plugged in 0 for the y value to get that particular x value. Does that make sense? All right, so same thing for the next one. So we want to find the 0, so we're going to plug in 0 for the y. So I get square root of 2x minus 5 equals 0. I'm going to square both sides, add the 5, and divide by 2. So I get x equals 5/2. So we plugged in 0 for y to get 5/2 for x, so 5/2 comma 0. I see a lot of people not taking notes. It's like 200 pages of hand-typed love, right? I put a lot of time in this. You at least humor me and take notes. What are you talking about? You have like these notes packets. Yeah, I have it all, but I just haven't printed it all. All right, so I have 0 equals 3t minus 6 over t plus 5. Okay, so I have 0 equals a fraction. So the only way for a fraction to ever equal 0 is if the numerator is equal to 0. So we're going to set our numerator equal to 0. It's kind of like you multiply the denominator over and it's gone, right? So we get 3t minus 6 equals 0. So I get t equals 2. So that's the point, 2 comma 0. Okay, so 0 is pretty easy. Just plug in 0 for the y to find the x value. All right, so the next thing we have is also an easy concept, but the definition is a little bit strange. So it says increasing function. A function is increasing on an interval if for any x1 minus x2 in that interval, f of x1 is less than or equal to f of x2. All right, and then decreasing, same idea. F of x1 is greater than or equal to f of x2. So I'm going to show you a sketch, and I think it's going to make sense. Okay? So let's say I have something like this, this, and then let's say I taper off and I go flat for a little bit, and then I go up. Okay? Increasing locations are going to be here, here, and here. All of those are going to be increasing. what's happening? The graph is going up, right? So as you read it like a book from left to right, the graph goes up. That's what it's saying. Okay, decreasing is going to be here, and that's it. All right, and then the last one is right here. This is what we call constant. Okay, it's just flat. So that's what those definitions are saying, but it's much easier to just see a picture and say, oh, I get it. It's increasing, decreasing, increasing, decreasing, and so on. Okay? So the first one says, on what interval is the function f of x equals x squared increasing? So if it's increasing, that means on the right side, see how it's going up? All right, so we're going to say it's increasing from 0 to infinity. All right, and then decreasing is going to be on the left side, so it's going to be decreasing from negative infinity to 0. Okay, some people are really picky about the endpoints. I tend to say that endpoint 0 is doing nothing. It's not increasing or decreasing. It's in between. So I just put parentheses on each one. Okay, does that make sense? All right, notice how increasing and decreasing, you're always talking about an interval, so it's always the x values. Like it's saying from x equals what to what, from x equals what to what. Yeah. All right, so the next one, so it says go ahead and graph that function. So you have x cubed, what was it, minus 2x plus 5? So x cubed minus 2x plus 5, so get your graphing calculator out and go ahead and graph it. And then use the standard 10 by 10 window. The next example. Doesn't like me today. Okay. And then go ahead and do your zoom 6, so it's that standard window, like I said. So when you graph it, so we all have the same graph. So does everybody have that graph? Okay, so it wants to know on what intervals we're increasing and decreasing. So what I will typically do is I will write the x and the y value, just in case there's a second part of the question that says, well, what's the absolute max, what's the absolute min, local max, local min. So we haven't talked about those yet, but we'll go and write the x value and the y value for these. Okay, so we have a little graph. Oops. And the graph looks something like it goes up and then it comes down and then it's like that, right? So we want to find this point and this point because that's where it's changing from increasing to decreasing. So maximums and minimums. So we're going to do that by finding the max and min. So we're going to do a second trace. We did this last time. And let's say we want to find the minimum. So let's find on the left of what we want, so hit enter. On the right of what we want, hit enter. Go exactly where you think it is, hit enter. So that point is 0.816 for the x, and then 3.911 for the y. So 0.816, 3.911.
Second trace on that part.
Minimum.
Okay.
So then you get on the left of what you want, hit enter, get on the right of what you want, hit enter, guess. What does it say? Okay, do your zoom 6, standard window. All right, so second trace, we're going to find the maximum. So when we find a maximum, we want on the left of what we want, so we hit enter. We want on the right of what we're trying to find, hit enter, and then it says guess. So go exactly where you think that maximum is. So it gives me negative 0.816, comma, 6.088. Oh, 0.089, we'll round. In AP Calc, you can actually round or truncate, which I don't like the truncating. I like the more precise. Truncate means just chop off. So I don't like it when we chop things off. What was it? What was the other number? 6.089. Okay. So I kind of write those there so I have them. Okay, so it asks for the interval on which it's increasing. So we're increasing from what x value to what x value. So we're going up from negative infinity to negative 0.816, exactly. And then we go up again where? Exactly. So I usually put a union between them. You could also just put a comma. It's fine. So negative infinity to negative 0.816, and then 0.816 to infinity. Okay, and we're decreasing. We're decreasing from negative 0.816 to positive 0.816. Okay, so you're always going from what x value to what x value. We're talking about the interval it's on. Make sense? Okay, so then we have this definition for relative maximum, which is also a local maximum, and so on. So it says a relative maximum. It says a function value f of a is called a relative maximum of f if it is the greatest number in a certain interval. So this is kind of a hard concept to understand. So basically, if you zoom in on a particular location, it's like at the top of a hill. Okay, so I always say it's in Whoville, which is weird. Like think Dr. Seuss in Whoville. If you zoom in, if there's a little hill there, you're good. So it doesn't matter for the whole graph. It's just saying in a particular location. So you could have like something going up, down, you know, something like this. And eventually it goes up forever. And this side goes down forever. There's not a highest point of all because this goes up forever, right? So there's not a highest point of all, and there's not a lowest point of all because the left side goes down forever. But there are general locations that are the highest in that area. Okay, so if you zoom in, like right here, that would be a relative max. Do you guys understand that concept? Okay, and this would be like a relative min. So there's lots of relative maxes and relative mins. We also call these local maxes and local mins. All right, but when you talk about an absolute maximum, an absolute has to be the highest point of all on the entire graph. So this one would have no absolute max. But something like that would have an absolute max, right? There's a highest point of all. Okay, so this one says, use your calculator to find all the local maxima and minima of the function x to the fourth minus 2x squared minus 4. What is the absolute max and absolute min, if applicable? So let's find it. So we're going to do x to the fourth minus 2x squared minus 4. Okay. So when you graph it, you should get a little W shape. This W shape is actually symmetric with respect to the axis. I don't know if that's actually what it's above the axis, isn't it? Oops, I keep doing that. No, it's below the axis, we're right. Okay, so we're going to find those 2 points, and they're actually symmetric. So one is a positive x, one is a negative x. Okay, so go ahead and do the minimum. And you can find either one, it doesn't matter. So about half of you guys do one, half of you do the other one. So don't do the one that I'm doing. You can do the other one. Okay, so when I did this, my calculator had a little bit of an error. And this happens a lot with calculators. Calculators lie to you all the time. So I have negative 0.9999995. Okay, what do you think it actually is? It's negative 1, right? Some of your calculators gave you negative 1.02, right? So that happened. I'm a genius. I just knew it was going to be that. This happened in the last class. All right, so basically, if you're not sure, you could zoom in on a particular area, and you could try to do it again, and it would give you a more precise answer. But it probably is negative 1, right? So if you can assume it is, that's fine. On the AP Calc exam, they always say you can round to 3 decimals. So if I wasn't sure and I was like, ooh, can't tell if this is the right answer, maybe it's rounded, I would do negative 1.000. And I'm like, I'm good. I did 3 decimals. I am correct. All right, so if you want to do that, that's fine. Okay, so this first one ends up being negative 1, negative 5, and the other one ends up being 1, comma, negative 5.
Yeah, I don't get that.
Why are they symmetric?
No, that's like when I put it in on my calculator.
Was it really close to that or no?
It was like, yeah, it was like negative 1.064.
Okay, does it say minimum on it? I'll check in a second. Maybe you didn't do the left, right, middle. So try it again. So you do second trace minimum and then try it again. All right, so when it talks about absolute max and absolute min, does it have both of them?
No.
No. So absolute max, we say none. We don't say infinity or anything like that. We just say none. All right, absolute min. We always, whenever we're talking about a maximum or minimum, so local or absolute, it doesn't matter. When you're talking about how high or low something goes, you're talking about the y value. So your absolute min is what y value? -5. And then I would say at x equals the y, x equals plus or minus 1. Or x equals 1 and x equals -1. All right, is there a local max?
Yeah.
Yeah, there is a local max, and you could find that by doing the same thing, do the maximum piece, right? So second trace maximum, and you'd be able to find that. So I guess maybe I should do. So it did say find all local and, so our local max, did anybody find it? I think you get 0, -4 actually, based on the symmetry. So we say -4 at x equals 0. And then the absolute min, we're also going to say local. So say local / absolute min. Okay, so we have everything covered then. All right, is that the last one? Oh, one more thing. Okay, so something, if something's continuous, that's the next thing we're going to talk about. If something's continuous, that means you can draw it without lifting your pencil. Okay, so there's a lot of graphs that we did last year that you could not draw without lifting a pencil. 1/x comes to mind. Y equals 1/x. Okay, that would be here and here. All right, that is not continuous. Okay, it's not continuous because you cannot connect those two lines without lifting your pencil. Okay. All right, one that would be continuous, maybe like the absolute value of x or some kind of polynomial, right? These would all be continuous functions. That one's not really a function because I messed up there. But like that, those would be continuous. All right, and then even and odd. An even function, the most basic one to think of is y equals x squared. It's going to be symmetric across the y-axis. So that's the fold line. If you can fold straight over, then it's going to be even. So that one that we just did, the little w, that was an even function because I can fold it across. That's why I said I knew what those other points were based on the symmetry. All right, but then an odd function, the most basic odd function is y equals x cubed. Okay, and that one's odd for a really weird rule. I'm going to show you what it is here. So see this picture? And you can do this with your book as well. Something's odd if you can rotate it at 180 degrees. So watch this little picture that I have. If I move it around and I get the exact same function, then it's odd. So if you rotate it 180 degrees, so you can always like turn your paper around to figure it out. Does that make sense? Let me make this smaller.
We don't do that, so do we?
No. Oops. All right, so we need to decide if these things are even or if they're odd. Get rid of that one. Oops. Nope, they could also be neither. All right, so the first one, we have 1/x squared. So if you aren't sure what it looks like, you can draw a little graph using a t-table. It looks like this. Do you think it's even or it's odd? Is it symmetric across the x-axis?
Yeah.
Yes. So this one's, or across the y-axis, I guess. So this one is even. Is it continuous? Right. because you cannot draw it without lifting your pencil. As much as you want those to connect to the very top, they do not. Yes?
So the one, like the first one you run your example is not used, that's not as well.
That one is odd because you can flip it. Yep. All right, so this is not continuous because there's a vertical asymptote at x equals 0. Do you see it?
Was
All
it
right.
possible for something to be odd and even?
No. That would be when we say neither. All right, so the next one. So if I have g of x equals the square root of x, actually it can be odd and even. If it's a circle, then it would be odd and even, which is kind of
So we
strange.
have to do that.
Yeah, we call that symmetric with respect to the origin, actually. All right, so if I have g of x equals the square root of x plus 5, it looks like the square root of x function, which is like that, but it's been shifted. It's been shifted left 5. So it's like that. So is it continuous? Yep. So it's okay if there's things that aren't in its domain as long as it doesn't skip over points along the way. So it's continuous, and it's neither. All right, and then if you graph this last one, you could use your graphing calculator if you want to. It has vertical asymptotes at 3 and -3. Do you remember graphing these last year? You guys hated them. And it ends up looking like a little U shape here. Oops, that is symmetric. I didn't draw mine very well. And then 2 there. So is it even or odd? Or neither? It is even. Is it continuous? No, not continuous. Okay, so there is a trick for some things on telling if things are even or odd. If you have a function that looks like 4x to the 4th minus 2x squared plus 5, that is actually even. And I can tell immediately looking at it because it's like this is 5x to the 0, and all of my powers are even. I have 4, 2, and 0. But if I have something where I have f of x equals x cubed minus 2x, just the first, right? That's x cubed and x to the first, that would be odd. But if you have one that's a combination of the two, that is neither. So you can tell pretty quickly on things if things are even or odd. Okay? All right, any questions on that? Yeah, let me pass out your homework.